I am Luca Todesco, aka QWERTY or UIOP, and you can find me idling on irc.crackspy.kim in channel chat, or on Twitter at QWERTY or UIOPZ. And yeah, I've been doing dependent security research for a few years now. I own my own company, and yeah, I'm the supreme leader of it, JSC International Research SRL. Most of my research has been in the privilege escalation part of things, but nowadays I mostly focus on browser exploitation. And right now my main target is JavaScript core, and this talk will go through why that's the case. And so yes, this talk is about a fictional character that is trying to get code execution on the latest iOS updates. Again, all these also applies to macOS. And our fictional character began by exploiting dumb use after freeze, back when the heaps were very easy to hack. But now more and more mitigations have been implemented by Apple, and so we need a fresh start. And the JavaScript core GIT compiler seemed a very good target for something that would resist and would be exploitable still, even with many mitigations thrown. However, obviously, more and more security features are being added, and so the battle is still going on. And so what is WebKit exactly? Well, it's Apple's open source web browser. It powers mobile Safari on iOS and Safari on macOS 10. It also powers Tesla's web browser as well as the PS4 one. And it's actually multiple projects, the most important of which are WebCore, JavaScript core, and WTF. And specifically, I'm going to start discussing WebCore, which is where our fictional character started his journey from. And yes, WebCore implements HTML parsing, DOM, SVG, CSS, and a lot of the remote code executions that have been seen in the wild have been DOM use after freeze. The reason for this is because in WebCore, many use after freeze are present due to the reference counting nature of the C++ runtime. And yes, the DOM is also very dynamic, and so it's very easy to run into object lifetime issues. And so I'm going to show you an example of a typical DOM bug. This is some random bug pulled out of Project Zero. And we can see that at some point here, we get a pointer to an object. However, no reference whatsoever is taken. And after a while, we run some function which happens to be able to trigger a JavaScript callback. And when that happens, if you look at our proof of concept code, we have two event handlers. And one of them, the selection start one in event handler 2, actually enters our vulnerable function. And again, these might trigger a JavaScript callback, specifically event handler 1, which will change the type of the object, which will invoke this function, which actually ends up freeing the inner text element object. And if you look back, inner text object is a pointer that we have in our stack frame that we saved without taking any reference. And so this is sort of the scenario that happens, and any use of inner text after our callback has run will be a use after free. And so yes, most DOM bugs share this common theme. So a reference to some object is stored in the stack, but the reference count is not increased. A JavaScript callback is able to execute and destroy the last reference of such an object, triggering a call to free. And upon return, use after free happens. Again, it's really important to note that reference counted object here is the keyword. There are other browsers like Chrome or Edge that do not use reference counted objects for the DOM, which are more hardened than WebCore to these sort of attacks. And back in the day, you could just use the fast malloc allocator for most of those objects. And Other than that, you would also have array buffer, backing buffers living on the fast malloc heap. And those buffers are a really convenient replacement because they allow you to get full read write access to a complete heap chunk from JavaScript. And the standard way of pulling this off is to replace the freed object with an array buffer, backing buffer, replace the vtable pointer, and you get array key control. But this will require a prior info leak usually. And so actually, I analyzed it a bit further, and I realized that sometimes the use after free can actually leave a dangling pointer to some C++ object inside some other C++ object. And this pointer might actually represent a DOM object that you can actually export into the JavaScript world. And when you do that, webquery implements a wrapper thing that essentially represents the C++ object within the JavaScript core virtual machine. And each of these wrapper will have one-to-one mapping. So one object only has one wrapper, and it's cached inline in the C++ object. So the conversion function, which is handled by 2JS, can actually read the JavaScript value from the freed C++ object and return it into our JS engine, and we can turn DOM bugs into JavaScript engine bugs like this. Further, you could also leak JavaScript values to many instances of this because marked argument buffer, object used by the JavaScript VM, also used to be in fast malloc, and string buffers would also be in fast malloc. And so if you were able to leak a string object pointer and corrupt the length to it, you could actually leak from the fast malloc heap, and by putting a marked argument buffer next to our string buffer, you could leak arbitrary JS values. And so you could get JavaScript object pointers out of it. And actually, these conditions seems unlikely to be viable to do, but many DOM objects allow you to leak pointers once you replace them with the array buffer, and as well as increase arbitrarily a control pointer. And I actually did this for a bug that would have a UAF against HTML document. And once you have the ability to leak JavaScript object and create a fake one, there used to be this very nice technique introduced by Cellulo in this Pratt paper, where you could just create a fake JavaScript object that represented a type array, and by just putting a controlled backing buffer pointer in there, you could reference any address and have full read-write primitives from within JavaScript. And this was really easy to pull off, and it was a really powerful primitive. And once you had read-write capabilities, you'd be able to just write inside the JIT area, which is mapped as read-write execute. iOS specifically has mandatory code signing, but this actually bypasses that. And yes, again, with a typed array, you can just write into it and remove code execution. However, and this is iOS specific, by the way, on macOS this mitigation is not present. The previous slide actually still works just fine on macOS. On iOS, they hardened this JIT mapping by separating it into two different regions, one of which is executable and the other is writable. And the pointer to the writable map is only ever stored inside an execute-only piece of code. So in order to be able to access the writable map, you are forced to call into that function. And this means a write anywhere primitive is not sufficient for code execution anymore, and you must use wrap or other techniques in order to invoke said function. And yes, I mean, it does make it harder to exploit WebKit bugs, but not by that much. But still, I mean, it's pretty sad because theoretically this is completely bad. Again, practically that's not the case for any device other than the iPhone XS. And it's not the case for macOS because this is not a thing at all. Additionally, Philip Pitzler, one of the main maintainers of WebKit, decided that the type array objects and butterflies will be put in a Via cage, which are a very large amount of memory that is reserved only for those, and any access, read and write to one of those objects will be masked. So you will or in the bits of the giga cage. And so even if you have read-write and you can control the backing buffer, that's only within a given giga cage. And so this technique is that, again, yes, only to giga cage memory, and butterfly pointers also were caged, but this was reverted, which means that we can actually use butterfly accesses to gain read-write still. However, this is not fully controlled, but it's still good enough for most scenarios. And Nicholas B actually used this for a public iPhone 8 RC exploit. And at some point, pointer poisoning was also used, which, if I remember correctly, was spectre mitigation, but it was removed with this commit. And actually, I remember seeing another commit saying kill it with fire. So I think they were not happy about that, and we just got rid of it. Additionally, I mentioned giga cage, and this commit is really interesting to me because they should start from a slide, which means ASLR. And yes, if you look at the dates, that's been a year and a half. So for 1.5 years, hyper-randomization was completely broken on both iOS and macOS. Additionally, another mitigation that was introduced is separated heaps. So every given object type in C++ is allocated to its own heap, and you're not able to type confused things anymore. So even if you found an object that's kind of like array buffer, backing buffers, still living in fastmalloc, you would still not be able to use that to replace C++ DOM object. And so things get quite tricky here because, yes, this prevents use after free bugs from being exploited in most scenarios. And so theoretically, the bug pass is completely bad, which is not really true because you can still exploit some of the use after freeze, but it seems really difficult to actually pull it off still. And it seems like it's more trouble than it's worth to keep pushing it. So we have to start again from scratch, from the very basics. And this time we're going to focus on JavaScript core, which is the JavaScript engine still with WebKit. And so my answer to the previous problem is to just shift to pure JS engine vulnerabilities. And I'm going to show you an example of what that means and exploitation of one of those vulnerabilities, which is particularly good. And so JavaScript core, again, it's a JavaScript engine. It has an interpreter called LLint and multiple GITs. Each GIT has different properties as far as compile time and throughput goes. And based on how many times your function is invoked, you will move from first interpreter and then to the baseline JIT, and then to the BFG JIT, then to the FDL JIT. And every time you go over, you optimize your code more and more in native machine code. And so we get to our bug. This bug was introduced fairly recently in February 2019, and it's a register allocator bug in the BFG JIT compiler. It actually resided in the string.prototype.slice GIT implementation, and this was introduced as a result of the JavaScript core team trying to shrink the object size of a string from, I think, 24 bytes to 16. So they introduced a very, very good remote code execution for a marginal gain in memory consumption. And this bug was found by Bruno Keith and donated to science, so only thanks to him for this. And this is what the vulnerable code looks like. This is code in the GIT that will be executed when a function contains a string slice operation. And this will emit the native machine code for that specific operation. And one thing to note here is that we have a conditional branch right there. And after that, we have a register allocation. But what is a register allocation? Why is it even needed? Well, the JIT code needs to use registers in order to perform logic on the native machine all the time. And registers are a limited resource. And so you need to have some sort of algorithm that assigns registers dynamically. And if you run out of registers, you need to spill them to the stack. And when you need them again, you have to fetch them from the stack again. And again, we have a register allocation right there, and potentially we need to spill those values to the stack. But we have a conditional branch just before that. And if the branch is taken, none of that code ends up running. Which is kind of an issue because the register allocator actually assumes that all allocations happen unconditionally. And the conditional branch can skip the allocation and the spill. And if the variable corresponding the supposedly spilled register is later used, uninitialized stack data is going to be fetched. Another thing about JavaScript core is that unlike web core, it makes heavy use of garbage collection. And most objects in JavaScript core, almost all of them, are garbage collected. And the GC is conservative on the stack, which means that once you enter the GC, it will actually mark from the top of the stack all the way the current stack frame. And another thing to note is that when you call a function with a variable number of arguments, you can create very large stack frames. And by doing this, you can actually store some value very deep into the stack. And when the garbage collector runs, those values will still be kept there, but the garbage collector is not going to be aware that those values are still potentially usable, because theoretically they aren't. It's just random garbage left over in the stack that should be initialized later on. And all the objects will be free. And so again, with our bug, we can actually end up having uninitialized stack data used as a JavaScript variable or some register that was being used by the JavaScript engine at that point in time. Which means that we can bring some value deep into the stack, and so not mark the garbage collector back to life. And this gives us immediate use of our free in JavaScript code. And this is actually good enough to get full code execution, but it's not going to be very reliable. You need to rely on the heap layout and the garbage collector running, which, I mean, you can do it with very good reliability, but it's not as cool as doing the type confusion one instead. And so again, the JIT will say have a variable in a register, and we'll put it on the stack. But actually, the branch will skip the put, and it's going to be uninitialized stack data. However, further accesses to that variable will still be interpreted as being of that specific type. And we can actually supply a JavaScript value of any other type via the uninitialized stack region, and that results in type confusion. And so here's how exploitation of such a bug looks like. So this is a function which is going to be run 10,000 times, and after you do that, it's going to be compiled by the DFG JIT. And this function begins by declaring a bunch of variables and an array, and then it's going to do a lot of accesses to the array. And every time you do one of those accesses, the stack frame is enlarged by 8. And I do this in order to have some space in case some other code happens to run and potentially overwrite the value that I carefully put in the stack beforehand. And afterwards, we will fetch from the arguments the value ARI1, and we will put it inside another JavaScript object. And when you do this, actually the JIT will have to prove the type of the object in order to perform inferred types. And so it will insert a JIT node that will prove the object's type. In this case, I will compile the function by running it 10,000 times with the not cell type. And if you see, the ARI1 value is actually going to be stored in RSI. And then we get to our vulnerable function called our vulnerable node, and we can see that we have our conditional jump, the JNZ right there, and then we have the register spilled from Brex and the RSI just following it. And of course, I mean, if you look at this assembly, it's really clear what's happening here. The branch actually will skip the location, but it will not bail out from the JIT. And so the register location and the spilling never happens. Following that, we access ARI1 through the reference from the object that we created, and we pass that value to a call string constructor node. And the call string constructor node will convert an object to a string. And when you do that, it will type it specifically to not sell. And again, we can make the JIT think that a variable containing some value is stored at a specific point in the stack frame, but it isn't. And the variable we can prove to be of a value of not sell type. And the proof is for the value which is not saved to the stack. So we have a time to check, time to use issue here, as the wrong value is going to be used when accessing the variable. And so we go back to our JIT code, and in the call string constructor node, you will again note that the argument is assumed to be proven to be not sell because of the prior proof that we did earlier. But again, we can specify any value as well as a sell. And this is interesting because of the concept of side effects. So in JavaScript, some operations might invoke callbacks or do some dangerous sort of operation. The callbacks are the nicest scenario here, and the most common of which are toString and value of type conversions. And the JIT needs to be aware of when these operations can happen, as they can be observed by user code and invalidate state, which is assumed not to change between JIT nodes. And so things that you could do is like change an object's type as the JIT code is running, change an array's indexing mode as the JIT code is running, and again, all type proofs done are still going to be considered valid, as you need to model for things that do this or not. And additionally, some operations might only invoke callbacks if their arguments are of specific type. And call string constructor in our case is very interesting because it's modeled to only side effect on sell use and untyped use arguments, because those two types are the types that represent arbitrary JavaScript objects, and in those you can redefine toString. However, for not sell use, they will still invoke toString. And this makes sense because as it's proven to be not sell, you can't redefine toString. And the normal toString implementation of booleans and integers, which are the two types represented by not sell and undefined and simple objects that are not heap-backed, they cannot redefine toString. And so doing toString is not going to be side effecting on those. And yes, so we have proven that the argument to our call string constructor node is known side effecting because it's not sell. However, we can redefine toString and perform arbitrary unmodeled side effects anyway because we pass in a different value at runtime. And so we converted a register location bug into a DFG JIT side effect when it's modeling issue. So this is significant again because DFG tries to optimize away redundant type checks, given that only few operations can actually change an object's type. And if none of those operations is ever encountered, it can be assumed that the object type is still unchanged and another type check is not necessary. And yes, this is kind of redundant, but by mutating object types, you can cause arbitrary type confusion. And so in our exploit, just before the call to string constructor, we do a fetch on a JavaScript array, hereby called float array, which is an array of doubles. By doing this access, we actually prove that the array contains doubles as members. And afterwards, once we run our string constructor node, we perform an unmodeled side effect. And our side effect here actually changes the float array's member at index 1 into a JavaScript object pointer. And this actually does a type conversion from the array of doubles into an array of JavaScript values. And in DFG, this is still assumed to be a double array because no possible type transition could have happened there according to GIT. And do note that we stored at index 1 a pointer to an object, and we access it considering to be a double. And so this is actually an address of equivalent type confusion, which allows us to info-leak any JavaScript object pointer as a double value, and then we can just convert it into an integer by using typed arrays and do integer arithmetic on it, and then store it back inside the array, still as double. And yes, when we do that, we have a fake object that's accessible at index 1 in our array. And this is interesting because of the specific layout of JavaScript objects. And so this is how an empty JavaScript object looks like. We have a header, and then we have a pointer to a butterfly. I'll get back to what a butterfly is a bit later, actually. However, if you create an object with a value in it at the very beginning, when you initialize it, you'll actually be stored inline, plus 0x10 in this case. And if you put more inline values, they will be all going in the inline cache inside the JS object itself. And so in this case, I put only integers, and you can see that are stored with the FFFF at the top, and that actually is a tag that marks the integer type. And now, instead, I create an object, and then I put it in one of the values, and you can see that at the very bottom of our object there, we have the pointer to the new object we created. Then we change it with the double value there, and you can see that we're going to have a tagged double, and which changes the bit representation of the double value in order to mark that it's of floating point type. Yes, we have these as our primitive that our bug gives us, which means that something like this ends up happening. And this results in a further type confusion every time we access our fake object between JSL and a tag double, as well as a pointer to an object and a pointer to a butterfly, if the fake object looks like this. And so we can just put our, wait, I think I was speaking about the wrong slide earlier. Okay, so we can just put a fake JS cell in there, taking into account the fact that it's going to be tagged. And then our type confusion actually moves to a type confusion between the pointer to a JavaScript object and the pointer to a butterfly. And butterflies are objects that look something like this. And so you have an array of values. We start by creating an empty object, and then we set an indexed value as if it's an array. And yes, butterfly is created, and the number 0, we have our 13.37 value. And in the JSL header, the indexing type will specify the type of the objects contained in the butterfly. So in this case, we set a double value in the butterfly, and so the type of the butterfly is going to be double. And so indexing type of the object is also double. However, now we add another object to another value to our butterfly, which is a JavaScript object. And when you do this, it will convert butterfly into a contiguous type butterfly, and you will have to tag the double value we previously put, and then put the pointer to our object there. And I mean, we have access to a fake object living in a object inline property cache, and actually, I mean, that alone is enough for code execution, but it's very convenient if you're in the business of writing exploits to have a standard set of primitives, so they can be plug and play in case a bug dies or something like that. And those primitives tend to be the address stuff and fake object primitives. And I mean, you can have the fake JSL header and control the indexing type of a fake object as well as the butterfly pointer. So deriving these should be possible. And my idea was to just set the butterfly pointer, the fake object itself. One detail about butterfly objects is that the length of the butterfly itself is going to be stored at a negative offset from the pointer to the butterfly itself. And to take this into account, I have to shift the fake object by 0x18 rather than 0x10, which is the size of the JavaScript object header. So we have some space to control the fake butterfly's vector length and public length. And so the layout ends up looking something like this. And then we put our fake vector length and public length in the container object as the value prior to the fake JSL header. And we also control the indexing type of our fake JSL to be of double type. And now we can access our fake object as an array, and all accesses there will result into a double value being returned to JavaScript. So yes, you have to take into consideration that double itself does not have any tag, but in inline objects we will have a tag, as you can see from the FFX at the very bottom there. And so yes, we end up with the ability to access the same memory area in two different ways, either as double or as JS value. And this is pretty much a perfect head confusion sort of scenario that ends up in giving us address of and fake object primitives directly. And so our address of primitive looks something like this, and our fake object primitive looks something like this. And yes, this is all there was to it until a few months ago, but now there's some extra details here. One slight detail is that we do need to fake a JSL header. And in order to be able to make a fake JSL header, you need to guess what's called a structure ID, which are the first 4 bytes of the JSL header itself. And the structure ID will define the shape of a given object. So the kind of inline properties it has, the kind of prototype it has. Structure IDs are necessary in order to create fake objects here. And in Sayul's white paper, this was accomplished by just spraying structure IDs, by creating lots of differently shaped objects. And in this specific case, JavaScript core would just create sequentially structure IDs, and you could just guess one of those, and it would be very reliable. And this is what most JavaScript exploits do, or did rather. Because on Saturday this February, faking a JSL got a hell of a lot harder. So what they did, they added some entropy bits to each structure ID. And if the entropy bits are guessed incorrectly, then the JavaScript engine is going to crash. And so you can't just spray and pray anymore, because those 7 entropy bits have to be guessed correctly. And each set of entropy bits is actually specific for each structure ID itself. So it's not just one value that's chosen at runtime, the first time you run the engine, but every time you create a different shaped object, different entropy bits are going to be used. And so yes, to create a structure ID now, you also need to be able to guess 7 entropy bits, and failed guesses mostly equal to crashes. Operations which will result in crashing are, for instance, accessing named properties, garbage collection visits, and really anything that you can think of will rely on structure ID being valid. And the public strategy for gaining read-write from a set of fake objects, of fake object and address of primitives, uses named property accesses. But even if we didn't, not having a valid structure ID will still very, very likely mean a crash when using a fake object. And so what this means is that this technique is actually completely dead, theoretically. But there are some things that you could possibly do in order to bypass this to this day. And here are some ideas for generic ways of doing so. So for instance, you could abuse differential behavior between specialized and non-specialized GIT code. For instance, in the FDL GIT code, it is possible to make use of looping direct code motion to move specific nodes before, for instance, some conditional branch or just return. And when the specialized code is run, it's gonna either just return do nothing, or it's gonna bail out to the interpreter instead, because the structure ID was guessed incorrectly, and the interpreter does not do looping direct code motion. So that node will never be executed, and so you will not have a crash because your conditional return will happen before that. And also, Sailo at 0x31con introduced the concept of inferred types, which could also be abusable, because you can create a real object and then put a fake object inside it, and then any access to the fake object through the real object will use a check structure node on the real object in order to prove the type of the fake object itself. And so you do not have to guess the structure ID in this specific scenario. But generic bypasses for this are possible and they do exist, but we're not going to talk about them now. But let's think about the bug we have at hand and see if we can leverage it for bypassing structure ID randomization with the bug-specific technique. And so let's go back real quick to what our bug was. We have an initialized stack variable access here, and the GIT can assume that the type contained in the stack slot is very specific, but we can specify any other value of any other type and cause arbitrary type confusion. And if we look at what the structure ID entropy mitigation actually added, well, I mean, once you have the ability to read out of bounds in the JSL heap, we can still look at valid structure ID, and we can just use that and not have to spray and pray or guess the 7 entropy bits. And an example of how to possibly do this with our bug could be by using the get by offset node. Get by offset is the GIT node that will fetch an inline property value from the object itself rather than the butterfly. And it doesn't perform any sort of bounds checking. It just relies on the type information being correct. However, if you're able to type confuse it, it will end up being out of bounds read. And yes, if we prove the type of a specific variable and then use our register locator bug in order to cause dfg-jit to mistrack its value and its type, we can put an object of another type and another shape in. And this is the code that tries to do that, and this is how it looks like. And so again, we begin with a lot of useless array accesses just to make our stack frame very large. Now we do a type proof. This time I did slightly different. I access an inline property on ARI1, and the dfg-jit will perform the type check before the get by offset node that is going to be put in the fetch of the B variable there. And then at the very bottom, we do another get by offset by fetching the A value of ARI1. And ARI1 has a proven type already from the type proof we made at the very beginning here. And I mean, no operations here, side effect. Slicing a string does not side effect. And so it's actually possible to reuse the type proof. And yes, actually, because of our bug, we can do a get by offset on an arbitrarily typed object now. And in this case, for instance, it's thinking it's going to fetch the A value from the JavaScript object OJ that created there that has 6, well, sorry, I can't do math, 1, 2, 3, 4, has 5 inline properties, and we'll fetch from the last one its value, and then create another object that only has 4 inline properties. And by using our bug, we can make the get by offset node fetch from an object that it thinks it's of one type, but in reality it's the other. And this results in out of bounds accesses. as the OJ1 object only has 0x20 bytes, but 30 bytes as size, but the fetch is from 0x30. And so we end up leaking the first 8 bytes of the next object in the heap. And this is what it looks like when this is JIT compiled. So we begin with our type proof, which is emitted by the DFG JIT to prove that the get by offset node at ARI1.b is correct. And then we trigger a bug, which will end up spilling to the stack RAX. And if you look at the check structure node that was inserted by DFG JIT there, you will see that RAX is the register that holds the ARI1 object. And so it's supposed to be spilled. And then we have our get by offset on ARI1 of proven type. And you can see that type is proven because there is no check structure. If you compile this code and go back, there is no check structure there. Only the check structure at the very beginning is going to be used. And yes, as per the assembly code, this results in out-of-bounds reading JSL heap. And this is actually the code that, well, the function here is what's going to get optimized. And this is the code that will trigger the optimization in the correct way and put the right values on the stack in order to perform this. The same function that you saw earlier, I copy and pasted it twice. So you can have two different functions that are identical in every way, but expect different typed objects. And I do this in order to be able to create a stack that is specifically controlled value that will contain the value even on the other function. And you need to have two different functions for this, because if you do one function and pass two different types in it, it will do a different kind of optimization, and this attack will not succeed. And this is the result running it on a recent webkit build. The bug is end-day, so it wouldn't work on the very latest version. But you can see that across different runs, the result is always different. And if you try to run this on an older JavaScript version, all those will be identical every single time. And that's the randomization going on here. And you can actually find the full code for the out-of-bound read implementation at this URL here. And so we get to the conclusion that getting code execution on iOS and macOS is tricky, as Apple has been very busy pushing mitigations. But given the right attack surface, it is still possible to find powerful enough bugs that result in full compromise. And JavaScript engines happen to be mind-boggling complicated, and there's always going to be a way to get code execution, in my opinion, even with pack and memory tagging. And I would like to thank specifically Bruno Keith, Nicholas B., Sailo, Philip Tidslow, and KJC for this. So if you have any question.
All right, so we have time for a few questions for Luca. Incredible talk. Thanks again for making the trek. Thanks, Shia.
Yeah, that was quite a blast.
See that question back here.
Is there sort of a roadmap for what we think Apple are going to do next in terms of mitigations? Obviously, PAC's the latest one, but is there any idea of where they'll go next? And also, thank you for the talk. I didn't understand half of it, but also more.
I'm sorry for that. So, well, specifically in WebKit, actually, there are mitigations that we can see already in the JIT, in the Git repo, where they will use pack in tag arrays as well as WebAssembly memory backing buffers, which kill read-write primitives that are currently being used, except for the butterfly one. But as for hardware mitigations and what's next in the whole ecosystem of iOS and hopefully macOS, which Apple doesn't seem to care about as much, memory tagging is the obvious one. I don't think this year is gonna be in their CPUs, but probably the next iteration of SoCs will have it. We'll see if we're gonna need a new job or if it's well, we as attackers are gonna need a new job, or probably defenders also, or things are still business as usual. And they are incrementally adding mitigations even with the current SOCs that they have. Specifically in kernel mode, they have very powerful primitives now to implement security features without necessarily needing to have new silicon in place. So, I mean, we'll see. But memory tagging, that's the elephant in the room as far as attackers go, as for what the future holds.